Hi, this is Ashim Datta from the Department of Biological and Environmental Engineering at Cornell University in Ithaca, New York. And this and a few companion short videos are meant to refresh the math that might have been forgotten because it was taken some time ago, math that would be useful in a heat transfer course or a diffusion related course.
In this module, we're going to solve the homogeneous Cartesian 1D equation, and we're going to use boundary condition on one end as the value given, but on the other end is not value given. Instead, it's the flux is equal to a multiplier of the value, and that's what will make things a bit different from the past.
In the past, we talked about solving this equation, d squared t dx squared equal to 0. So this is like what you did in calculus, d square y dx square equal to 0. So t is my independent variable. Now we solve this for uh, uh, two boundary conditions, and the boundary conditions looked like this. T at x equal to 0 is t1, and t at x equal to L is t2. So what we want to do here is solve it for two different boundary conditions. One side I will keep it as same, but the other side would be different. So this is my other boundary condition is equal to some constant h times t at x equal to L minus t infinity. Now you may wonder, where does this come from? So these represent a very important common physics, but we're not getting into the physics part. So from the physics, at least the situations that we would consider, these parts are all constant. So this is a constant, this is a constant, and this is a constant. And there's reason to have the negative sign, so we will keep it there. So the 2 points in this video are, because this boundary condition was changed to this one, then the solution for this case will no longer be valid, and there will be a different solution for this set of boundary condition. That's 1 point. And the other point is, because this boundary condition looks a bit involved, it's algebraic, the process to do the algebra to use this one is also just a tad bit different, and so we have to do this a little more carefully. So those are the two reasons for doing this one. So let's get going. If we solve the equation, we get dt dx equal to c1 some constant because the second derivative was 0, and then if we integrate one more time, we get c1x plus c2. Okay, so if we use the first boundary condition here, this guy, so if we use that one, then we get t1 is equal to c1 times 0 plus c2, which gives me c2 equal to t1. Notice that this other one is a bit different. So how is it different? Instead of the value of the function being given, here I have the derivative of the function. It's evaluated here, and that is equal to the function itself evaluated at x equal to L. So let's try to do this here. So let's see if we put 2 asterisk here. So that's the second boundary condition. So for that, I write minus k times dt dx at x equal to L. So realize that dt dx is unknown, and t at x equal to L is also unknown because the function itself is unknown right now. So this is my function. And so I write dt dx, which would be c1. If you take dt dx of this one, you get c1 is equal to h times this quantity. So every so often somebody will write h times t at x equal to L is TL minus t infinity. Now this would get us in big trouble, because what is TL? What is TL? Notice that this meaning of this part is t evaluated at x equal to L. So then this part, it should be t, that's this one, evaluated at x equal to L. So in other words, c1x plus c2 evaluated at x equal to L minus t infinity. So then this would be written as h times c1L plus c2. So this is x evaluated at x equal to L minus t infinity. So that is the meaning of this t evaluated at x equal to L. If we bring in something like TL, what is it? We are bringing in our own symbol, unknown, so then we need additional equations for this. Otherwise, we cannot solve it. So this is completely wrong and meaningless. And this is the part that we need to be careful in using this kind of boundary condition, because what it's saying, this term is t evaluated at x equal to L, just like here dt dx evaluated at x equal to L. And so now we can complete the algebra. We can write our purpose is to solve for C1 is equal to h times C1L plus h C2 minus h t infinity. And so we solve for C1 is K1 plus HL, bringing C1 on this side, and then bringing the rest of it on the other side, HT infinity minus HC2. And so then I get C1 is equal to HT infinity minus C2 over K1 plus HL, and sorry, there is no K1, and so C2 is known. So this C2 is what? C2 is T1. So H times T infinity minus T1 over K plus HL. And so C1 is known, C2 is known, so we plug in the solution. So my solution then is T solution for this set of boundary condition is t equal to c1 x. So c1 is this part, h times t infinity minus t1 over k plus hl times x plus c2 is equal to t1. So this is my solution. Now you might recap that for this boundary condition, the solution was t is equal to t2 minus t1 over L times x plus t1. Let me make sure it satisfies the boundary conditions. If I plug in x equal to 0, I get t1, and if I plug in x equal to L, then I get t2. So it satisfied. So this was my solution, and now because of the change in the boundary condition, because of this boundary condition instead of this boundary condition, then I get a different solution. So that is one reason we did this one. The other reason is using this boundary condition that is more involved than just the value given. Here the derivative of the function is related to the function at x equal to L, and that has to be done carefully like it is done here. These are the two reasons for doing this one, and when the value is given, it is generally the easiest. When it's not, then it's just one important step that has to be done carefully. Thank you.